All right, our last speaker in this session is Johan Castañeda Jaimes. Johan's been working this summer with Jeff, and today he'll tell us about their project together, Hidden Star Formation and AGN in a local ULERC.
Thank you for the kind introduction, and I'd like to thank everyone for showing up to hear all of the amazing student talks today. So yeah, I'll just get right into it. So my target, as Gwen mentioned, is a local ULERC. In fact, I've assembled a collage here of other local ULERCs. And a ULERC, also known as an ultraluminous infrared galaxy, is a galaxy that's characterized by having an infrared luminosity greater than 10 to the 12 solar luminosities. And what you'll notice about all of these ULERCs, especially within the low redshift limit, is that they're all either mergers or they're merger remnants. And so it's pretty clear that there is some correlation between having such pronounced infrared emission and linking it to all of the intense starburst activity and potential AGN accretion that occurs during the merger phase of galaxy evolution. And so that brings us to my target. My target is not a famous ULERC by any stretch. And so it's an interesting target in the sense that it has two resolvable cores, which are not necessarily present here in the Hubble image, which is in the optical. When looking in the infrared, the first sort of look into this galaxy came from Spitzer, and it came from this, from looking at it through IRAC. And so you can see clearly here that the two cores are resolvable already, and there is some diffuse structure nearby, but you can't really say much about the morphology of the galaxy. Nowadays, we can do better. We can point at the galaxy using the mid-infrared instrument on JWST, and what you can identify here is the presence of these three little starburst clumps within the northern core, as well as this pretty prominent AGN within the southern core. And we can even get a much more fine look into this galaxy by looking at integral field spectroscopy data from the medium resolution spectrograph on JWST. And so we can resolve all three of the starburst clumps within the IFS data, and we also get a pretty good look into the AGN within the southern nucleus. And so this brings us to some of the unresolved questions that face this galaxy in particular. So with the improved spatial resolution, as well as the improved spectral resolution, a natural question to ask is to sort of try to answer what exactly is the morphology of both of the nuclei. What features are present there? What do they look like? And what parts of the galaxy are they present in? Second question to ask is to resolve or to try to probe how AGN dominated the second nucleuses. So it's understood from previous literature, especially from this paper here, from Leslie 2014, that the southern galaxy could have some starburst activity. It's currently ambiguous, but this northern galaxy for sure is going to be dominated by starburst activity. And so trying to resolve this tension within the southern nucleus is an important question to consider going forward. And in addition to that question, this Leslie paper also introduced the idea that there could be a potential AGN-driven outflow within the southern nucleus. It could also be explained by rotation from some other gas component, but hopefully with this IFS data, we can resolve this tension in the future. So I mentioned that we're using IFS data to try to understand this galaxy. And so the beauty of having IFS data is that it allows us to construct a spectrum for each pixel or a collection of pixels. And this is a nice visualization of sort of how one would define an aperture within an IFS data and then construct a unique spectrum. So what you're looking here is you're looking at an extraction region in green within the northern core pointed at one of the starburst clumps, and then another extraction region pointing at the AGN within the southern core. And you can already see that there is some interesting variation in the spectra, which can be attributed to different physical components, either linked towards star formation or towards the AGN. And so once we extract a spectrum, we have to go about fitting it. We want to apply a quantitative value to the different features within the spectrum. And so I'm going to briefly walk through all the different components that go into fitting this mid-infrared spectrum. And so to start off, I'm going to discuss what the continuum components are. So the continuum captures all of the light that's coming from either different dust grain distributions that are within the line of sight between the telescope and the galaxy. So These could be components that are coming in from the overall galaxy disk. It could be components that are coming from starburst clouds or from narrowline regions, or from the torus associated with the AGN. And so the way this is modeled is effectively by modeling black body curves for different dust grain distributions at different temperatures. And we're also modeling direct starlight continua and any accretion disk continua that one might see. So on top of the continuum, we then go about fitting all the dust features. So the dust features here sort of represent themselves as these broad purple, sort of not quite Gaussian, but they're fit with a profile known as a Drude profile. And these dust features are driven by the presence of these dust molecules known as polycyclic aromatic hydrocarbons. So this is a very idealized representation of one of them. They're usually chained together, and they can come folded, they can come in a planar structure. Sort of the messy nature of these molecules results in a lot of these really interesting blended features within the spectrum. But the main driving point behind trying to model this molecule is that it takes in UV light that's being emitted from young stars, and it's reprocessing it into infrared light. And so that makes it a very good tracer for trying to find star formation within the mid-infrared. In addition to dust, we also model all of the emission lines. And so I've color-coded a few of them here. There are about 40 of them within the range that were provided. And so the most generic form of these are forbidden lines or other fine structure lines. And so these can be used as element-specific probes into the ISM. We also have coronal lines. So coronal lines are characterized by having very high ionization energies, and this makes them very useful for trying to probe the radiation field in different parts of the galaxy. And then in addition, we're also looking at molecular hydrogen lines, which allow us to probe into the gas phase kinematics of the cloud. So you put them all together, and then you get this spectrum fit, which isn't quite perfect. There are some features that aren't accounted for, but for the sake of modeling the dust and for the sake of modeling the emission lines, this is good enough to actually begin to probe some of the more coarse features within the galaxy. So we have observations with the MRS instrument of both of the cores. And during this talk, I'm going to show two diagnostic plots that we created for some of these broader extraction regions. So we're looking at the southern nucleus as a 1.8 arcsecond extraction region. We're also looking at the northern nucleus through a 1.7 arcsecond extraction region, and we've made smaller 0.3 arcsecond extraction regions for each of the starburst clumps. So once we've extracted the spectrum, the first thing we did is we plotted them and we scaled them such that we could see any initial variations that stick out to us as sort of initial lines of inquiry into trying to understand what features might be worth looking into that seem overly peculiar when compared to other LIRGs. And an easy thing to sort of probe initially is to try to look at the hardness of the radiation field. So what you're seeing right here is you're seeing the ratio of the fluxes of the sulfur 4 over the neon 2 line, as well as the neon 3 over the neon 2 line on the y-axis. And so emission lines, when emission lines emit radiation, they're particularly sensitive when the photon energy distribution is on the order of the ionization energy of the line itself. So neon 3 and sulfur 4 are both higher ionization energy lines than neon 2. And so what this conveys is that when you look at a distribution of points here, and I should mention that the points that are being displayed on here are points that were constructed using Spitzer long spectroscopy. So these are all Spitzer values, and I've highlighted the value for this particular target in this yellow circle. And so points that lie towards this side of the plot are indicative of having a harder energy distribution. So we took our extraction regions, we constructed this diagnostic, and we end up seeing that the northern nucleus, the 3 starburst clumps individually, as well as the larger extraction region, all tend to be on the softer side of the energy distribution. Meanwhile, we see a very hard value for the southern nucleus, which falls in line with what we would expect. We would expect an AGN to have a harder energy distribution anyways. So this is nice to see, and it's falls in line with expectations that have been set by literature. The other thing that we looked at is we looked at the ionization properties of the dust grains. And what we're doing here is we're taking the relative intensity values of the 6.2 pH feature over the 7.7 pH feature on the x-axis, as well as the 11.3 micron pH feature over the 7.7 micron feature on the y-axis. And these are also Spitzer values. Now, I mentioned earlier that PAH molecules can come in a variety of different shapes and sizes. And so what this allows is it allows for the decomposition of certain molecules. And depending on which spectral feature you see, those can be related to different physical processes. So in particular, the 6.2 micron feature and the 11.3 micron feature are both ones that are associated with either rotational or vibrational modes associated with ionized grains. Meanwhile, the 7.7 micron features are associated with neutral grains. And what's particularly novel about this diagnostic plot is that Spitzer was not able to constrain this for this particular target. So these are all novel data points. We end up seeing that the three starburst clumps as well as the northern nucleus tend to have more neutral grains. Meanwhile, the southern nucleus has more ionized grains, once again, falling within the expectation that is set by suspecting that there's an AGN within the southern nucleus. Now, that's a very broad approach at looking at the morphology of the galaxy, but we can get a lot more granular by virtue of the fact that we have the IFS data. And so these are preliminary spaxel maps. This is of the neon 3 line within the northern nucleus, and this is of the S3 molecular hydrogen line within the southern nucleus. And initially, everything here seems normal. There doesn't seem to be anything all too peculiar. And this is because we're looking at the flux values for both of these lines. But we ended up going through it and fitting each of these lines with a one Gaussian component, which is a rather naive fit. And we ended up finding that there was some velocity shearing present within this neon 5 line at 14 microns. And when we fit the neon 3 line at 15 microns, we ended up finding that the full width half maximum of the line fit tended to have this jagged discontinuity. And it's within the same region as this sort of blue shifted component. And sure enough, when we actually poked around and we looked at the flux values, we picked two frames. We picked one frame that was blue shifted, sort of it's offset by 0.01 microns away from the expected neon 3 line center. And we also looked at the redshifted component the same way, and we end up seeing this very prominent blue shifted and redshifted component. In some locations, it's very sharp. In other locations, you can kind of detect a broad component. And so this sort of brings us to where we currently are within this work. So we've identified 3 new starburst regions. We've probed the radiation field, and we've probed the sort of the dust grain ionization for both of the cores. And I didn't mention this on the previous slide, but the outflow / rotation feature that we ended up seeing within this slide is actually similarly positioned to the one that was seen in the Leslie paper. So there's some evidence to suggest that we're looking at perhaps the same feature, maybe looking at different scales or looking at different sides of it. And so work still needs to be done to try to identify and constrain is that, whether or not this could be sort of a bipolar AGN outflow, or maybe that's part of the disk that we're seeing from one of the progenitor galaxies. And so we need to characterize that outflow and that rotation feature. We also want to generate PAH dust feature maps, and we want to integrate some newly taken near spec data for this target. So, there's lots of sort of avenues of investigation for the future for this target, and I'm really excited to continue working on it. So that's where we're at right now, and I'm happy to take on questions.
Hey, thank you, Johan. Any questions? Anna.
That was really interesting, the new outflow feature that you found. And you mentioned that it could be either an AGN or this outflow. What kind of observations could tell which way it goes?
Yeah, so we found this feature very recently, as in this week. So we haven't really probed too many lines. So one thing that we want to do is we want to try to identify which lines this outflow feature is present in. Just by looking at the data cubes themselves, they're in iron lines, they're in argon lines, they're in the other neon lines, and they're in some of the molecular hydrogen lines. And so trying to identify which one of those lines has it perhaps most prominently featured in is one way of going about it. We also want to generate moment maps for each of these blue shifted and red shifted components. And then depending on how sharp the feature, how broad the feature is, those are the types of things that we would use to try to characterize the outflow.
What do you mean by that? Is that like a common rotating disk or what is it?
It's expected that both of these, so it's a merger, so both of the progenitor galaxies are expected to have been spiral galaxies. And so it could be part of that disk that got broken up during the merger. It could be some other gas component that is also being flung around. And so it was ambiguous in the Leslie paper because they did not have the spatial resolution in their IFS data to try to characterize it. And so that's a whole body of literature that I haven't gotten into yet, especially because there are different kinds of outflows, and trying to identify one of them could get, my understanding is that it can get very messy to try to identify them. So yeah. I don't know if that answered your question. Or...
Other questions for you? Right, let's thank him again.